Welcome to module 12 of database management systems. In this module, we will talk about the formal relational query languages. In the last couple of modules, we have discussed about SQL at length, introducing it, dealing with the intermediate level of SQL features, and then exposing to some of the advanced features as well. The foundational mathematical model of SQL, the query languages, are to be discussed in this present module. So, this is what we had done in the last module. In the current one, we will work to understand the formal query languages primarily through relational algebra, and then we will also take a look into some of the calculus aspects, tuple relational calculus and domain relational calculus, and we will show by example the equivalence between the algebra and the two calculus. So, formal relational query languages are of three types. One is known as relational algebra. This is procedural in nature. So, we specify what operations need to be done to achieve the result, and the whole formulation is based on set algebra. The second formal query language is tuple relational calculus, which is non-procedural and is based on predicate calculus. The third one, the domain relational calculus, is a minor variant of the tuple relational calculus and is also non-procedural and predicate calculus based. So, we will start with the relational algebra. In the relational algebra, it was created by Edgar F. Codd at IBM in 1970s. So, you can see that it is quite an old formulation. It is a procedural language. It has 6 operators. We have taken a quick view of these earlier. In this module, we will look at them at length. The select, project, union, set difference, Cartesian product, and rename. We will also look at few derived operations like intersection and division, which can be expressed in terms of these basic operators, and each one of these operators can take one or two relations as input, and they produce one relation as a result. So, we start with the select operation, which you know has a notation sigma. Subscript p is a predicate. It is called the selection predicate, and within parenthesis we have a relation R on which this predicate applies. So, it is defined as a set where you collect all the tuples, all the rows designated by T, and you specify that T belongs to the relation. So, it already exists in that relation and it satisfies the particular selection predicate. So, any tuple that satisfies this predicate is included in the result, any that does not satisfy is excluded from the result. P here particularly is a propositional calculus formula or expression, where we have different terms that are connected by conjunction or and, disjunction or negation or not. And each term by itself could be something like this. It is an attribute, operate and an attribute, where operators are different comparison operators, one of the any 6, or a term could be an attribute, operator, a constant. So, given that we can write any expression which is a predicate, and applying that we can select the tuples from the relation R which satisfy this predicate. So, here we show a simple example. Instructor is a relation, department name is an attribute, within quotes physics is a constant or literal. So, this selection show will select all the tuples where the attribute department name is equal to physics, and all the others will be eliminated. For reference, I have also quoted here the example that we had shown at the time of introducing relational algebra. So, you can see that here we have a more complex propositional term, propositional formula, where there are two terms, the A should equal B and D should be greater than 5. So, in the selection result, both of these conditions must be satisfied by all the tuples which feature here. So, this is the first operation that relational algebra has, the select operation. Next, we move on to the second operation, which is a project operation, where a relation can be projected in terms of a number of attributes. So, pi is the notation, R again is the relation, and the subscripted A1, A2, Ak are k attribute names, k has to be at least 1, and these attributes will be retained in the relation. So, the result is defined as the relation of k columns by erasing all the columns of R which are not listed amongst this A to k. Naturally, if you erase some columns, it is possible that two rows that were distinct in those columns, but are identical in A1 to Ak feature in the relation. Since every relation is a set, no two copies of the same tuple are allowed. So, the duplicate rows will be removed from the result. Remind you, this is in contrast to what SQL does by default, where duplicates or multi-sets are allowed by default. Here we are talking about the formal relational algebra, where it is purely set theoretic. So, duplicate rows on projection will be removed from the result. So, we have an example from the instructor relation we had seen earlier. We are projecting ID, name and salary. So, we are removing the department name which also exists in the same relation. And as a reference, you can see the example that we had seen earlier while introducing the relational algebra, where projection is done from 3 columns A, B, C into 2 columns A and C, and this results in two rows which are identical, and therefore, in the final result one of those, the duplicate one, is removed. Moving on, the third operation is quite simple. It is set theoretic union. So, R union S, where R and S are two relations, are set of tuples which either belong to R or belongs to S or belongs to both. The condition is, you can take union if both these relations have the same arity, and the order of the attributes must satisfy that every corresponding attribute must have compatible domains. So, if I talk about the second column of R, and if we talk about the second column of S, they must be of the same type, and this must hold for all columns that the union forms, that is all columns of R as well as S. Otherwise, this operation is not defined. So, as an example, we show that to find all courses taught in fall 2009 semester, this is the query where we do a selection to find all tuples which are taught, which represent courses taught in fall 2009 semester from the section relation. We do a projection to get the IDs of those courses only, and the second row tells you the courses that are taught in the spring 2010 semester, and we do a union to get courses that are taught either in fall 2009 semester or in spring 2010 semester or both. This is how the union is performed, and this is the earlier example repeated here. Set difference is again just a simple difference of sets R minus S, where a tuple belongs to R and it does not belong to S. So, you remove all the tuples belonging to S that exist in R to get R minus S. Again, they must have the compatibility of having the same arity, and attribute corresponding attribute domains must be compatible. This is an example to show to find all courses taught in fall 2009, but not in spring 2010. So, as opposed to union in the last slide, you do a set difference to get this result. So, this is how you can use set theoretic operation to get different relational results. This is also the result from the earlier example. Set intersection can be supported, is supported, but it is not a basic operation, because as it is defined by all tuples which belong to both R and S, it can actually be computed by applying set difference twice, and certainly for set intersection also the same assumption about arity and compatibility of types hold, and this is the earlier example. Next is Cartesian product, where we take two relations, and for the Cartesian product we juxtapose one relation with the other. So, T is a relation from is a tuple from R, Q is a tuple from S, and we put them side by side to get a T Q row in the Cartesian product R cross S, which basically mean that you compute all possible combinations of tuples from R and of S. It is assumed that the attributes of R and S are disjoint, that is, the schema of R intersection schema of S is null. If the attributes are not disjoint, then we must use renaming, which we will soon see, and here is an example that we had shown earlier of R and S computing R cross S. Cartesian product is a very useful operation, particularly for computing join, as we have seen in SQL already. Rename operation basically allows you to rename some expression attribute into another. So, the operator is row, and you have an expression to which you gave the name x, and that is how the renaming of you can have multiple attributes of x as well. Division is another operator in relational algebra that can be applied between two relations, but it is a derived operation. So, it says that if I have, so let me just show you by a little bit of sketch, that if I have two relations which R, which has a set of attributes z, and S, which has a set of attribute x, such that actually the set z is a superset of x. So, z has more attributes, the relation R has more attributes. So, if you take the difference of attributes between z and x and call it y, then we are interested what happens on these remaining set of attributes y. So, this is what we have, this is my x set of attributes, this is where x occurs, this difference is y, this whole set is z. Now, in this what we want is we want to in the output we want a relation having only the y attributes such that for every tuple in that relation, if I consider all the tuples of S, then their cross product must be a part of R. So, for every tuple here, if there are say 4 tuples here, a tuple here must have all these 4 tuples along with it in the result. If it does not have any one or more of them, then that tuple will not feature in the final result. So, the result of a division is a relation T y that include tuple T if tuples T r, that is the part of the tuple that appear in R, and on that on the y part, the difference part, it matches, so that you have that T r x is equal to T s, where T s actually exists in S. This must happen for all tuples in S. So, division is a very good interesting operator, which is often required for coding different queries. So, it is a derived operation. Let us take an example. Let us say this is the relation R and this is the relation S, and I am trying to compute R divided by S. So, what I want is over the attributes of this is therefore x, this is x, this is attribute y, attribute set y. So, all over x, all the values that I have, I must have those values in the relation R. If I do, then the attribute, the particular tuple matching on the attribute y goes on to the result. So, alpha goes on to the result because you have both alpha a, alpha 1 as well as alpha 2 in the set R, in the relation R. Beta 1 is there and beta 2 is also there. So, beta also goes into the relation, alpha goes in because 1 is there, 2 is also there, but gamma will not go in because I have gamma 1, but I do not have a tuple gamma 2 in R. If I had gamma 2 in R, that will go in the result. So, if I can say it again, the whole of the relation S must happen over the x attributes of R. Consider these two together. If that happens, then the attributes on y, the tuples would be chosen, and that is how we get the result having alpha and beta. Let us look at one more example. So, this has got R has 5 attributes, this has x has 2. So, this is 2 attributes x, these are 3 attributes y, and what I have to look for is those tuples in R where the values over y would be same, and I should be able to get the whole table of x over whole table of the relation S over the x attributes. So, if we look at here, this is a 1 b 1, a 1 b 1 here, these are identical. So, this particular tuple will go into the result. If I look in here, this tuple will go into the result. But if I consider this tuple beta a gamma, which has a 1 over d e, but beta a gamma does not have b 1, it has b 3. So, it will not go into the result. So, if you conceptually look at, that is the reason this is called a division, So, you get this here, you get this here. So, this is like the way we divide, that this is the whole, and wherever it goes in, if the tuples that are identical on the y set of attributes, we will collect them into the final result. So, this is the division operation, which by which we can compute the students who have taken both A and B courses with instructor 1 will be found out from this division operation. So, formally speaking, a basic expression in relational algebra consists either of a relation in the database, which is a instance, or a constant relation which does not change, which is given, and then we have 6 operations of union, set difference, cross product, selection, projection and renaming that can give us all sorts of different relational algebra formula and also the derived operations, and whatever we have seen of SQL can be expressed in terms of these relational algebra formula. Now, relational algebra is not something totally unique. The same thing can be done in terms of other formulations also. A second formulation which is also used is known as tuple relational calculus, which is non-procedural. Relational algebra was procedural because you are actually doing the explaining what the operations are, you are detailing out what the operations are. In tuple relational calculus, you just specify what the condition is, you are specifying what this condition is. So, those tuples which satisfy this condition form the relation. So, P is a predicate. So, whatever T satisfies the predicate are included, and if A is an attribute, then T A will denote the value of the tuple on attribute A. A could be a single attribute, it could be a set of attributes also, and T is a relation that belongs to R. P is, as said, it is a predicate calculus formula. So, it could be a set of attributes or constants. This I am just included for your help. If in case you have become rusted with predicate calculus, you can refer to them. A predicate calculus is a set of attributes and constants. It is a set of comparison operators, the 6 of them. There are a set of connectives. These are all same as the propositional calculus. There is implication, which says if x is true, then y is true. If x is false, then the whole thing is true vacuously. And what makes it primarily predicate calculus is the fact that it has existential quantifier, which says that the formula there exists T belongs to R, Q T holds if I can find at least one tuple T which satisfies Q T. Similarly, there is a universal quantifier where I will say that for all T belongs to R, Q T is true if for all tuples of R, T satisfies Q T. So, this in tuple relational calculus, all conditions, all predicates are formula of this kind, and with that we can represent any relational set in full. There is a word of caution, because it is possible to write tuple relational calculus expression that can potentially generate infinite relations. Now, infinite relations are naturally not representable. For example, if I write simply this, that R is a relation, and I write this predicate that not of T belongs to R, which is basically complement set of R. Now, a complement set of R potentially may be infinite if the domain is infinite. So, such expressions, tuple relational expressions, are not acceptable as a part of the design. So, whenever we want to do this, we would like to guard this by putting some additional condition, and we have to make sure that any expression that we have in tuple relational calculus is a safe expression, in the sense that it does give me finite number of tuples in the relation. A third formalism that exists, that is used, is known as domain relational calculus, which is also non-procedural and equivalent in power to tuple relational calculus again, which is very similar to tuple relational calculus. The only difference being, if you just recall, tuple relational calculus, we are writing collection of tuples T such that P T, that is the predicate P is satisfied by T. Here, instead of writing a tuple variable T, we expand it out in terms of all its components. So, we write the values of the different components of T over different n attributes and write it as a n tuple. And so, here instead of having one variable T, we have n variable x 1 to x n, and therefore, the predicate is formed of these n variables, where x 1 to x n represent the different domain values, domain variables, and that leads to the reason for the name domain relational calculus. Now, of the three formalisms that we have seen, we will not go into direct mathematical proofs, but in the next couple of slides I just show that they are equivalent in nature. What means that if I can write an expression in relational algebra, then it is possible to write an equivalent expression in tuple relational calculus and in domain relational calculus and vice versa. So, if I can write an expression in any one of these formalisms, then there are equivalent expressions in the other two formalisms as well, which is probably very easy to see between tuple relational calculus and domain relational calculus, because one is just representing the whole tuple as a single variable, whereas the other is representing in terms of n domain variables. So, their equivalence is pretty much very similar, except the fact that your predicate calculus formula has to change, but it is not so obvious for the equivalence between relational algebra and the calculi. So, we just show a few examples of the basic operations. For example, say select operation. So, I am just not showing the proof, I am just giving you some example cases to show. So, relation R has two attributes A B. This is what you wanted to write in relational algebra, that you want to collect all tuples where B is equal to 17. Naturally, in tuple relational calculus, you can easily write the first condition is you are doing it on R. So, T must belong to R, and your condition is B should be 17. So, this predicate will represent the same set or the same relation as in tuple calculus. In domain calculus, there are two components A and B. So, you have to say component taken together must belong to R, and the component B must be equal to 17. So, you can see that it is pretty straightforward to see the equivalence between a relational algebra expression involving select and the corresponding tuple calculus or domain calculus expressions. This is through an example, but you can certainly easily generalize this as a proof. Similarly, for projection, if we do a projection on A, then all that we are trying to do is we are trying to create a new relation where only the A attribute exists. So, in the tuple T, the A attribute exists, and if I have projected and got this tuple T, then in my original relation R, there must be some tuple P such that on the attribute A they match, they are same. So, it is the same thing in relational algebra, we said that keep A and erase everything else. Here we are saying that if we have been able to get a tuple T which has a value T A, then there must be a tuple P in R which has the same value over the same attribute. So, this condition is equivalent representative of the projection, and the same thing can be written in domain calculus. You can go through it carefully and convince yourself. You can combine these as in the relational algebra as well as in tuple calculus. So, here you apply one operation and then the other one, selection then projection. Here you are combining this is part of projection, This is also part of projection, but this condition has come from the selection and get a total predicate calculus predicate, which will give you the tuple calculus expression for this combined expression of relational algebra. Domain calculus will certainly happen in a similar manner. Union certainly is straightforward, so you can do it yourself. Set difference is again very straightforward, because that is in fact in set theoretically whatever operations we have there. Relational algebraic definition itself is a tuple calculus formula. You can expand them out and write in the domain calculus as well. Intersection plays out in the same way, tuples that belong to both R and S. Cartesian product is little bit more involved, because all that you are saying here is, if I have a Cartesian product, then if that product has a tuple T, then there must be a tuple P in the relation R, the left relation, there must be a tuple Q in S, the right relation, so that the final tuple T matches P on the A attributes, the B attributes, that is the attributes of relation R, and the components of T matches the tuple Q in the attributes of S. If all these conditions happen together, then naturally this tuple T is a valid tuple for the Cartesian product. So, you could take examples and work this out and convince yourself that these are really equivalent. We can define a natural join in a similar way, which I will leave it as an exercise for you to convince yourself that this relational algebra expression for natural join indeed has similar equivalence in tuple and domain calculi. Division we just showed as a derived operation. We have not showed how in relational algebra you can write division using the other operations. I will leave that as an exercise as well, but here what I show is in tuple calculus how you can write division using the quantifiers. So, here you can see that here for the first time we do need to use the universal quantifier to make sure that while I divide, that the whole of the table of S must be available against the part of the tuple, part of the y attributes as we said, that will be collected in the result. So, to summarize, we have discussed primarily the relational algebra with some examples. We have introduced the tuple relational and domain relational calculus, and through a set of examples we have shown that we have illustrated that the algebra and the calculi are equivalent, and I would request you to work out more examples to understand the equivalence, or if you are really enthused, please try out proving their equivalence formally as well.